how we're going to finish out this year. So I do have information on final exams, so we are required to give some sort of end of the year assessment. In a class like this, that an exam clearly makes the most sense, as I don't know what kind of a paper or project we'd be expecting you guys to be able to complete. The format for the exam is going to be, I'm going to take 2 to 3 questions from each of the tests that we've done, exactly. So I've made a page on PowerSchool here under our bulletin board called Exams. Has a little bit of a rundown, so we're going to take exact questions from previous tests, pretty much 2 to 3 questions from each test. I've attached the versions of the keys from the test that I took the exam questions from, because we might have had 2 or 3 different exam or test versions floating around for some of these tests, so I didn't know which one, what hour it took anymore, so I'm just like, forget it, I'm just going to give everybody the keys and just blah, blah, blah. All the questions are equally weighted. You have to show work. Here's the test keys. We are going to have, for Chapter 15 will also appear on the exam. I've included the Chapter 15 test or test key for what I would have given if we were going to do a test for Chapter 15, which we will not be doing. Thoughts on exam format if we have to have an exam? Does this seem reasonable?
Wait, if we have to?
Well, I mean, since we have to.
Oh, okay.
Sorry,
I prefer not to do it at all.
I understand. I would have been happy in that scenario as well.
Is it good? I think your idea would be best.
Okay.
I like the material that you provided.
For Chapter 15, I don't feel like, with everything else you have going on at the end of the year, that we need to do homework checks for Chapter 15. So I posted all the materials for 15. We'll talk about Chapter 15. I'm going to tell you what you could be doing for Chapter 15, but you do not need to turn it in. I will not be checking it. It just feels like that's one more headache that you don't really need at the end of the year. At the end of the day, if you can do the problems from the test key that I've left you, you should be fine for the final, which I think is probably enough.
Yeah.
Are the blank tests also on there?
I didn't put the blank ones on there, I just put the keys.
Okay.
But
Could you put the blank one on there? Just so we can practice the problems.
Sure. Okay. But that'll be a minute before I can have it.
Yeah, of course.
Does everybody feel okay with what we'll do for 15? So no new grades are going to come in, basically. You're at where we're at. We'll talk about stuff from 15, but we're not going to have any more assignments or any more grades coming in or out. So kind of your score is where your score is heading into the final. So you know exactly kind of where you're at.
Will it be a Chapter 15 test?
The 15 is only going to appear on the final. I see no reason in doing another test. We've done 6 of them already, I think.
Yeah.
I think that's plenty to get a good feel for kind of what we're able to do this semester. 15 on the final and no chapter test seems perfectly reasonable, as I think that probably most of us are going to be swamped here in the last month of the school year. It tends to get kind of hectic with other projects and papers and APs and IBs and all this other exams and all that. I don't want to inundate you with a bunch of other busy work, and I think at this point I feel pretty good about where you are at or what you can do and not do. With the final just being my last piece of making that final judgment that I have where we're at. Does everybody feel okay there? That feels all reasonable. We feel good. Nobody's mad about having no more grades to worry about for this class outside of the final, I hope. Very good. Let me ask you even this. As far as the chapter 15 stuff goes, would you rather just kind of like look at the lessons and work on the test review or the test and just like have me shut up and get out of your way? Or do you want to kind of go through it, me holding your hand and like we normally do? It's up to you. Like it doesn't bother me one way or the other.
What's the first option?
I mean,
To just
holding your
you have the test, you have the lessons, and like it is mostly topics you've seen and
Is it going to be like the exact same numbers from the test on?
so that yes.
Okay, it'll be like.
So like if like problem 8 was on there, I basically just kind of copied and pasted number 8. And I changed the format a little bit depending on what the instructions were to like get it all inside of a single question rather than like here's a question, here's some instructions, and here's a couple of questions. And maybe like I took 2 easy questions and turned it into like part A and part B of one question on the final, but they're like exactly the same numbers.
Okay.
Sarah?
What is this chapter on?
Chapter 15 is on exponential, logistic, and logarithmic equations.
I don't remember if it was in there, but it's like it's in there.
Yeah, I mean we can still do it. That's fine, not a big deal at all. I just thought I would ask since we're kind of handling the end of the year a little informally because we're not taking any grades on anything. But we'll do it. That's fine. No biggie.
It's like doable. I know.
Well,
What do you think?
Yeah.
I mean,
What do you recommend?
I think the majority of this should be pretty familiar. Like I would plan to do like, I don't know, like the first 10 pages or so of the lessons today, or more maybe even, depending on like how quick we can kind of go through these things. But I think it's here. You know what? We'll just start, and if you guys are like, okay, like like more or less, we can figure it out. Okay. So.
These are way too expensive.
All right. So section 1 is about exponential and logistic functions. So we'll start with exponential functions, which are just things that can be written in the form a times b to the x. The a is like our initial value. The b is called the base of the exponential. And the value for x is like our exponent. Everybody's okay with that? Just a little bit of vocab. One thing to keep in mind, that the limit for something like this, as x approaches negative infinity, so there the x is getting to be a smaller and smaller number, right? Remember, if I have a negative in the exponent, what does it do? It makes a reciprocal. So if b is bigger than 1, It's basically heading towards 0. And similarly, then if b is between 0 and 1, so it's a fraction that's less than 1, like a half or whatever, there you know that if you multiply a half times a half, it gets smaller. You get like a quarter. Right? Half times a half is a fourth. So there, as x gets bigger, the overall function gets smaller and heads towards 0 again, right? So like if you're looking at the graph, this one kind of looks like this. And this one kind of looks like that. Everybody's okay with that idea? I'm going to skip plugging numbers into an exponential function because, you know, like, what's the point in that? You can plug numbers in for x and type in your calculator and a value, right? All right. Suppose that we have an XY table that looks like this. And we ask you to find the equation that fits this table. I'm pretty happy to do that. This is not actually too bad in this case because I have the one where x is equal to 0. So if I plug in 0, 3 into y equals a times b to the x, I get 3 equals a times b to the 0, and anything to the 0 power is 1. So that just gives me that a is equal to 3. I can then take some other point, say 115, and use that then to solve for b. And that's not too bad, right? It gets slightly trickier if, say, you're given only 2 ordered pairs. So say we're given these ordered pairs, and we're asked to write the exponential function that passes through these. So what I'm going to do here is I'm going to take my general form for an exponential function and create a system of 2 equations. So each of these is an xy. So equation 1, I can say 48 equals a times b to the negative 3. And I can say 12 is equal a times b to the negative 1. Now I'm going to solve this system by elimination. Unlike for a linear equation, when we have our variables that are being added or subtracting, when we eliminate, we like multiply and then add the 2 equations together to cancel things out. Here our variables are being multiplied together. So to do our elimination, we're going to be doing division. So I'm going to divide equation 2 by equation 1. I chose to make equation 2 the numerator because the exponent on b in equation 2 is bigger than the exponent on b in equation 1, right? Negative 1 is bigger than negative 3. So what I'd have there then is 12 over 48 equals a times b to the negative 1 over a times b to the negative 3. So that simplifies down to 1/4 on the left-hand side. The a's cancel out. And then to simplify b to the negative 1 over b to the negative 3, I can subtract the exponents. So negative 1 minus a negative 3 is 2. So that's how I got the b squared. You guys remember that? And then we can square root both sides to get my value for b. However, I can ignore the negatives because the base of an exponential must be positive and not equal to 1, or else it's not an exponential. It's either something else or nothing. So there's my value for b. Once I have that, then it's easy to solve for a. So I'm going to plug that value for b back into equation 2, because the arithmetic will be a little bit easier. 1/2 to the negative 1 is just 2. And then I divide both sides by 2 to get a equals 6. And there we go. Is everybody okay? So far, so good? Now, one of the things that we've noticed about these exponential functions is, depending on what the values are, the base of my exponential can be written as a different number, right? You see that? Like, for example, first example, the base of the exponential is 5. The second example, the base of the exponential is 1/2. It's oftentimes useful to be able to compare two exponentials together. It's much easier to do that if they have the same base. So one of the ways that we can do that is using a special number called Euler's number. That's in reference to the mathematician Leonard Euler. He's back there on the Hall of Fame there. The symbol we use to express Euler's number is the lowercase letter e. And the value, the decimal value for that number e is about 2.71828, yada, yada, yada. We would have derived that in your Algebra 3-4 class. We're not going to do that right now. The main point, or the big takeaway here, is that we use this value for e often to describe things that are changing continuously. So, like, especially in the sciences, if you have something that's changing, has exponential change or growth going on continuously, we like to use e. So what this allows us to do then is we can also write an exponential function, any exponential function, in the form f of x equals a times e to the kx. So just for an example here, let's say we had our previous one, where I have 6 times 1/2 to the x. And I want to rewrite this as in this form of y equals a times e to the kx. So a has to be 6. No change there, right? E to the kx, we know, is the same thing as e to the k to the x. And that needs to be equal to 1/2 to the x. So we just need to really find the value for k that makes e equal to 1/2. Do you guys remember from your Algebra 3-4 class how we might solve that equation for k? Well, if your variable's in the exponent like this, you'll need to use a logarithm. Which logarithm would we need to use to cancel the exponent base of e? The natural log. Very good. The symbol we use to abbreviate the natural log is ln. So that k is going to be the natural log of 1/2. And if we wanted a decimal for that, we could go into our calculator and do the natural log of 1/2. And that's about negative 693. So just to kind of illustrate this, the e to the negative 693 is the same as 1/2. So what this would allow us to do is really compare two exponentials that have different bases. We can compare their k's, which will tell us a little bit about their growth and decay. We say that we have exponential growth when the leading term is positive and the b value is bigger than 1 or the k value is greater than 0, depending on which form you're using. And then we have decay. The a value is positive, and then either the b is between 0 and 1, or the k is negative. A story problem example. I'm just going to read the story problem aloud to you guys rather than writing down all the details.
That's fair.
It says, given the population of a certain city in 1990 is 782,248 people, and the population in the same city in the year 2000 is 895,193, and assuming that the population growth is exponential, in what year will the population reach 1 million? So what I'm going to do, you'll see that I've already turned the x coordinates into 0 and 10 from 1990 and 2000. You guys okay with that? just keeps every other numbers a little bit smaller. I'll have to remember that when I solve for x later on, I have to add 1990 back to it. But it just makes the arithmetic a little bit less onerous. So we're going to do what we did just before. So right away, I know that the A is the 782,248 since the x-coordinate is 0, right? I can then solve for B by plugging the other point in. So I divide both sides by 782, yada, yada, yada. And then take the 10 through to both sides. I can ignore the plus or minuses. If I go to my calculator, I can press Math and then Command 5 to get the nth root. And then just so I don't goof up any parentheses, I'm going to use that fraction command to write this as a fraction. So I get about 101,357, yada, yada, yada. Now, one way we could solve this, if we're looking at when this gets to 1 million, is we could do this graphically. So if I'm ever in a situation like on ACT or whenever, where I don't know how to solve the equation that I'm being asked to solve, I can usually just graph both sides of the equation and find the intersection, which is what we're about to do. So even if I don't really know how to solve it algebraically, I can do this geometrically with my calculator and I'll be okay. So my window, I know from 0 to 10 I'm not at 1 million yet, so my x value has to be bigger than 10. Let's make it 50. I don't really know how big it's going to need to be. I mean, I do because I have the answers written out in front of me, but let's pretend that I don't know. Now, the initial population size is 782. That would be the smallest that my population could be. Is the initial. I'm going to just round that down to a nice even 750,000. And I'm interested in when it gets to 1 million. Well, I want it to be a little bit more than 1 million because I want to be able to see the intersection on my calculator. So I'm going to do like 1,250,000. Go up by 100,000 or something. Seems good. And then I'll hit graph. So there's my 1 million line. Here's my population curve. It looks rather straight, doesn't it? The reason it looks so straight is because that b value is very, very close to 1. If that b value were bigger, it would look more curvy, but the closer that b value is to 1, the straighter your exponential growth is going to look. What I'm interested in is this point of intersection. To find that with my calculator, I'll press second and trace. I'm going to select the intersect command. And because I have just 2 curves and only 1 intersection, I can just ignore all the questions and just press enter 3 times and it spits it out as 18.22. And that would be years after 1990, or basically sometime during 2008. Now, you can say, Mr. Kulik, like, that was a lot of googly-gok to go through to find that when I could have just solved for this algebraically. I remember how to do that in my Algebra 3-4 class, and I would say, you're right. Now, we haven't talked about logarithms yet, which is why I showed you how to do it with your calculator, but all of you have seen logarithms in your Algebra 3-4 class. What we could have done is you could have divided both sides by that 782,000. And then to get the x by itself, we'll take the logarithm of both sides. But which logarithm should we use? Trick question, it doesn't really matter.
Yeah.
Which would be the fastest one to use, though?
That's a better question.
Would be log base 101,357, the same exact base that matches the base on my exponential. So we'll do, to get that in your calculator, you can press math and scroll down to the bottom and pick the log base option. And I'm going to use the answer command because that's my b value right there. Saves me some typing. And I have 1 million divided by 782,248. And there we go. Nope. What just happened? That's not right. Let's just, I must have not counted my zeros right or something. Okay, so that's that. And then I needed log base of that number of this number, and then enter. There it is. I don't know, I typoed something before, I don't know what it was. But there's that same 18.21 number. Everybody cool? Either way of doing it is fine. Now, a topic that you didn't see in your Algebra 3-4 class would have been talking about logistic growth or decay. So let's define that a little bit more carefully. And then if b is between 0 and 1, or k is negative, then what we have is logistic decay. So a logistic function differs from an exponential one in a couple of very important different ways. In an exponential function, you have one horizontal asymptote, right? So you have just something like this. Your HA is y equals k. Here, though, we have two horizontal asymptotes, one at 0 and the other at c. This one is because the limit as x approaches negative infinity goes to 0, and this one is because the limit as x approaches positive infinity goes to c. This is for growth, by the way. They flip for decay. But it doesn't matter. They're still the same asymptotes, just like the limits just flip, I should say. Yes? Of course! So let's just graph one of these bad mama jammas on our calculator and just kind of see what's going on. Sound good to you guys? Do we get a picture of what this is looking like? Because right now Mr. Kulik's kind of described it to me. But I haven't seen what the picture of one of these before looks like. So just FYI, let's see here. So C is 10, A is 3, and B is 0.6, right? That I just pulled from that. So this is a decay one. P value is, oops, I'm sorry. It is a growth one. Since the V value is less than 1. But let's see what this looks like when we type it into our calculator. So clear this mumbo jumbo out of here. And I'm going to use the fraction option so that I don't have to worry about goofing up some parentheses. And we'll set our window here. And let's just do, I don't know, we'll do like -20 to +20 or something, should be plenty. And then we'll go the y's. Well, I know it's going from 0 to 10 are where my two asymptotes are, right? So I'll just do like -5 to 15 or something. So there's my logistic. Everybody cool with that? Just as an aside, if this was the logistic decay, let's just say this was 1.6 instead of 0.6, you'll see that it's basically flipped. Instead of looking like an S, it kind of looks like a 5 or whatever. Or instead of looking like a 5, it looks like an S. Right? Just the two ends of the graphs are following the different asymptotes. That's all the difference between the growth and decays. Basically, sloping down is decay, sloping up is growth. Right? Yes?
Can I go back?
Absolutely. All right. So let's do an example story problem here using this. So the population of a city can be modeled using the logistic growth equation. As follows. Where P is the population of the city T years after 1950. At the beginning of what year will the city have 1 million people? Why would this logistic model maybe give us a better descriptor of a population? So if you think about a population of things, are they going to continue to grow forever? What if you have, so you think the population of people on Earth is going to continue to grow forever? Like we're just going to keep having more people than we did the day before?
Not forever.
We're never going to run out of resources?
So we all die.
Right? At some point you're going to hit the carrying capacity for your environment, which really you can't make any more organisms because there's not enough resources to kind of sustain them. And so like the growth rate and the death rate kind of balance each other out, and you just kind of get the sustainability, which is what the logistic curve is looking like, right? It grows and then it slows. Or if you're practicing a sport, most like athletic improvements would follow like a logistic curve, where you get better right away, but the longer you're doing it, the slower, like the harder it is to get better. So like there's lots of things in the real world that are like kind of grow exponentially, but then kind of like hit a barricade. That's kind of what's going on with this logistic function. So I just typed this into my calculator, and then I'm going to type in 1 million. Then we'll set our window. So 0 is 1950. I don't know how long this is going to take. I'm going to pick 100. I'm hoping within 100 years this thing gets to 1 million, but I don't really know. I'm just taking a guess and stab in the dark. The initial population is this 1 million, or I don't know. It's not 1 million something, right? Something though. So let's just pick this like. I don't know, let's do like 750,000 to 1.5 million. I don't really know. That seems. The point of the matter is I just need 1 million to be covered in there somewhere. So there's my growth curve. Oh, I'm so dumb. Here, I'm so dumb. I'm so dumb. I'm so dumb. The asymptotes are between 0 and 1,425,000. Those should be what I pick as my mins and maxes. Instead of doing 1,425,000, yada yada, I just did 1.5 million. That's a much better looking picture, right? There's my logistic curve. There it's coming through. Nice and pretty. Find the intersection. Second. Trace. Oops. Second. Trace. Intersect command. Enter, enter, enter. Bada boom, bada bing. 79 years after 1950. So, that's the same thing as what? 2029. How would have we tried to solve that algebraically? Do we have all the tools we need to do it? betcha. Do you guys want to do it algebraically? Let's do it. Why not, right? Don't hurt nothing. So I'm going to start by just dividing the 1,425,397 to both sides. Now, what I would do is I would do the reciprocal of both sides to get the variable out of the denominator, the fraction on the right-hand side. And since the numerator now is 1 over there, that's even better, as it just gets rid of the fraction on the right-hand side altogether. Then I can subtract the 1 over, and then divide the 21,783 over. And let's get a decimal there, because I'm not going to do that all with fractions anymore, right? And then we'll do the log of both sides, the natural log, really. Yes. OneNote froze.
OneNote's my favorite. Said no one ever.
I like OneNote, and I had like no problems with this particular freezing with the old crappy computer. But they gave us this really nice new ones, and boy, they are not. The OneNote is not nearly as stable on it.
None of the teachers like
Oh,
them.
yeah,
All the
yeah.
teachers complain about them.
I mean, it's a much better machine. Like the processor speed, like you can see, it's noticeably faster. Like all the performance is much better, but like it seems like there's a lot of software plugging going on.
You should go work for Microsoft.
True.
Why would I want to do that?
Time to go get up. Oh man.
So I have something like that, right? So we take the natural log of both sides, and I'm just going to finish the rest of this out on my calculator. I'm not going to write any more down. You guys are cool with that?
Yeah.
So natural log of both sides, and then divide by that negative 0.49782. And there's my, I think I lost the decimal point in there. And I copied this from the beginning here. Yeah. So there's supposed to be an extra 0 there that I lost. So if I divide that by another 0.1, there's my 79. Sorry about that. I lost the 0 on my decimal in that exponent there. But that was a transcription error. Feel okay there? That was section 1. Section 2 we're going to look at exponential and logistic models. So our first one is the exponential, and one glitched on me again. Don't get it. I was doing just fine for like 45 minutes, and then all of a sudden it wants to be a what? You know? Oh. Well, you guys told me you wanted me to do this, so we're doing it.
Yeah, I did break. I didn't know it was
I didn't realize one section.
I had an AP test.
What?
I had an AP test.
Okay. So this is our exponential population model. So P naught is just the initial population. R is the percent change. As a percentage, that's why it's being divided by 100 is to convert it into a decimal. And then T is time, but it needs to match the rate on your percent change, right? So if your percent change is 8% per year, then your time is in years, right? If your rate is 12% every 7 years, your time is 1 is equal to 7, 2 is equal to 14, 3 is equal to 21, right? Your unit T is in 7-year increments. Is there another model here? Are we just going to do the same thing the whole way through? And we're just going to do the same thing the whole way through. So where is the logistic? Anyways, I guess all right, let's burn through a couple of examples and get out of town with our hair still attached. All right, so I'm going to just read through some examples here. So let's say we have these two population models. That are given here. So first things first, are these growth or decays? Should be easy, you can do it on site. Good. You need to look at the base of the exponential. Since that number is bigger than 1, it's growth. Since that number is less than 1, that's decay. You feel okay there?
Yeah.
Okay. And I might ask you then, what is the rate of change? So to do that, I'm going to take the base of the exponential and set it equal to the base of the exponential in my population model. And solve for R. Okay with that? Or if we do the other one, that's going to be negative 3, 3, 1. Is that okay? Just solving for R. I did it in my head instead of using a calculator. We're good? Subtract by 1 and divide or multiply by 100, right? It's like algebra 1 stuff.
True.
Cool. So let's say then we have a different situation. What if we ask to determine the population model with an initial value of 15 that increases at a constant rate of 6% every year? Well, when I hear that, I get this. And when I simplify that down, which turns in 15 times 1.06 t, where t is in years. What if instead it was 6% per 6 months? So one thing I probably don't want to do is to still just write it this way. Where I have to write the t in 6 months in increments. So when t is 1, that represents 6 months. And when t is 2, that's 12 months. That's pretty annoying. So one thing I can do is I can either, if I want to do per year, I'm going to change t to 2t. Because how many times does 6 months go into a year? Twice. Or maybe I want to do t is in months, in which case I would change t to t over 6, because how many months, or how many times does 6 months go into 1 month? 1/6, right? So I would write it like this. Or I would write it like this, depending on what the question was what the rest of the question might be asking about. But that allows t to represent, like, if t is 5, that's 5 years or 5 months. It doesn't mean like, oh, if t is 5, that means 5 times 6 is, you don't have to like go and do another conversion afterwards or whatever. You get what I'm saying? So that's like a weird thing that can happen. That's just kind of like, it's not that weird, but it's like inconvenient. You end up getting the wrong answer. You're like, why the heck am I getting the wrong answer? And it's like, well, it's because your unit is in like 8-month intervals and increments, and that's really kind of a silly way to write it. Let's say, suppose that we have a colony of bacteria that's in a petri dish, and that culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. Okay. So, yes. Of course. we got initially 120 bacteria. It doubles every 3 hours, so doubling is a 100% increase, right?
Yeah.
Everybody's good with that? That makes sense to everybody? It does if I say so.
Yeah.
So if you think about it, if we plug into our formula 100 in for R, the base of that exponential then becomes 2, which is exactly what doubling would mean. Is that okay?
Yeah.
You looked a little uncertain to me, but so I can say right away that P of T then is 120 times 1 plus 100 over 100. And then would I probably want to write this, in hours, right? Where T is in hours? You guys agree with that? Probably. So what should my exponent be? Should it be 3T or T over 3? T over 3,
Yeah, that's right.
right? Because how many times does 3 hours go into 1 hour? 1/3. Okay? And then we can solve that for 400,000. You want to just do that on your calculator, that's okay. You could solve it algebraically because I know we know enough about logarithms to do that. But for the sake of argument and matching the notes, let's do it this way. I don't know how long this is going to take. I don't know, let's just go from 0. Can't be less than 0 time, right? And I'll go out to 100. I don't know, I don't doubt it's going to take that long. That's a pretty fast rate. Doubling. And then it has to be over 400,000, so I'm just going to do 500,000 as my maximum. Going up by, I don't know, say 50,000 or something. Let's take a look. There's, whoa, that's a pretty steep growth. Okay, there's my point of intersection, second trace, intersect, enter, enter, enter. And I have 35.1 hours. Whoa. That is it's a bacterial explosion. Another very common example of these exponential models is in radioactive decay. You guys talked about this in your chemistry or science classes probably. So radioactive elements typically decay. They slowly emit particles or energy until they turn into a different substance. Typically we measure the radioactivity of a substance by half-life. That's the amount of time it takes for half of that radioactive sample to decay into a lighter, different element. Or different isotope, I guess. Sometimes they just turn into the same, like carbon-14 just turns into carbon-12. Sometimes it's just isotope, and it's not element to element. You know, like uranium turns into something different. Is it lead? I don't remember. Anyways, so let's just look. Let me just read an example. Suppose the half-life of a certain radioactive element or radioactive substance here is 35 days, and you have 10 grams initially. Find the time it would take for there to be only 1 gram remaining. So our initial is 10. Our rate is negative 50%. It's negative because it's decay, right? It's decreasing. And 50% because if you lose half of something, you're losing 50%. Per 35 days. And we're looking for when P of T is equal to 1. 10 times 1 plus negative 50 over 100. And then what should my exponent be? It's per 35 days. Should it be t over 35 or 35t? I want t in days probably, right? Yeah, t over 35. I wouldn't want to do years or months there. That seems inconvenient given the 35 days. Okay? So that could simplify down, right? And then we can just graph and find our intersection. So 10 times 0.5 to the t over 35, and then 1. So I don't know how long that's going to take. Probably potentially a long time, right? 35 days to get half of it gone. You know, like 35 is 5, 70 is 2.5. You know, another 105 is 1 and something. So I'm going to do over 2. I'm going to go up to like 200. That'll get me there. The minimum I can have since it's decay is 0. And the maximum, well, that's the initial amount I started with, which was 10. Go up by 1s then. Just hit the ground. So there's my decay. Whoop, whoop, whoop. There's my 1. So there's my intersection. Second trace, intersect command. Enter, enter, enter. 116.3 days or thereabouts. And then let's do one with a logistic. The logistic ones are not going to be situations where we'll force you to write your own logistic model. We'll give you a logistic model and just ask you to work with it. So for example, you start a bunny petting zoo. You determine the population of bunnies on your farm can be modeled by the equation B of t is equal to 800 over 1 plus 99 e to the negative 0.5t, where t is measured in years. How many bunnies do you have initially? Well, what time is initially? 0. So if I do that, e to the 0 is 1. 1 plus 99 is 100. 800 divided by 100 is 8. 8 bunnies. What is the maximum sustainable population of bunnies on your farm? That's the limit as x approaches positive infinity of b of t, which is going to be this piece. As t gets very, very big, it's going to be a very, very big negative number, which basically means that this piece is going to 0 down here. So you basically are left with 800 over 1. 800, which is exactly when we defined a logistic function, how the limit was working, right? Part C, how long will it take to have 500 bunnies? Well, that's calculator time, my friends. We're all friends here, right?
I don't like eating.
Best friends. Yeah, I think so too. And I don't really know how long to do this for. Again, t is time, so I don't know, like 50 years. I can't imagine my bunny farm hasn't maxed out in population in 50 years.
Mr. Cole, you have to keep extending
Yeah. Well, then it's not, my model shouldn't be logistic anymore if I'm going to do that. And I know my maximum is 800, so I'll go like 0 to 1,000 or something. That seems good. So there's my bunnies, my cute little bunnies.
Bunny, bunny, bunny.
There's 500 of them.
Oh, yes.
Enter, enter, enter. 10.2 years. And this feels like a good place to call it quits. You guys were done.